This is Group 19, Damien, Jeff, Tyson, and Clément. We are going to be presenting our work on applying machine learning to identify malicious URLs. We will first present our problem, then discuss our dataset and data processing, then discuss our models and our qualitative and quantitative results before concluding with a demonstration.
According to McPhee, global losses from cybercrime reached nearly $1 trillion in 2020. Cybercrime often involves the use of malicious URLs that host unsolicited and harmful content. Sometimes, the malicious nature of a URL is obvious, such as when the URL has improper formatting or when it contains suspicious phrases. However, hackers are becoming increasingly inventive at hiding the malicious nature of URLs. Also, malicious URLs come in many variants, each with different features. The objective of this project is to implement a deep learning model that can navigate all of these nuances and detect malicious URLs. If successful, our team's machine learning model could be embedded into software to block malicious URLs before they can be clicked.
We now move on to the dataset and data processing. In terms of the dataset that our group used, we were able to identify an open source database hosted on Kaggle of over 651,000 URLs, where the following screen recording displays how we were actually able to download that as well. As you can see, the data downloads as a CSV file, in which the URL types are benign, phishing, defacement, and malware. An issue with the data, however, is that some URLs have an HTTPS, HTTP, or www at the front and others don't. To correct this inconsistency, we had to remove these prefixes from the URLs. The following graphic displays the quantitative breakdown of URL types in the dataset. It is worth noting that our team is only interested in identifying if a URL is malicious or not. As a result, defacement, phishing, and malware URLs were reclassified and lumped together as malicious URLs, with the new breakdown shown. This reclassified data was then fed into PyTorch using a 70-15-15 training test validation split. As we previously saw, after the reclassifying, there were more benign URLs than malicious. Thus, duplication needed to occur, the results of which in the training validation subset are shown here. Now, why duplication, might you ask? Well, because there were significantly more benign URLs, we now prevent the model from being overly inclined to classify things as benign. Finally, after splitting the data and performing duplication, we transformed each URL into a vector. In these vectors, the entries are integers whose values correspond to the original characters of the URL. These tokenized URLs serve as the input to our models.
Based on what we've learned in class about training on text data, we chose LSTM and GRU architectures. For both of these, we varied the following hyperparameters: the batch size, the learning rate, the number of epochs, the size of the hidden state, the size of the cell state for the LSTM, and the pooling applied on the hidden states. Ultimately, a GRU model with the following hyperparameter settings performed the best in the validation set, with the Adam optimizer, max and mean pooling, 28 epochs, and a hidden size of 50. This GRU model's architecture is detailed in the following graphic. As you can see, it consists of one GRU layer followed by one linear classification layer at the end. Additionally, prior to inputting the tokenized URLs to the GRU, one hot encoding occurs. The training curves of the best model are shown here. The loss curve is rather noisy but gradually goes down, and the training and validation accuracy both move up consistently over the epochs. We can also examine some of the predictions our model is making on a random sample of the test set, which generally seem reasonable. For instance, our model correctly identifies that the fourth URL with an IP address in a .ip page is suspicious. We can't see any mistake on these particular samples. Both benign and malicious URLs are classified correctly.
The overall test accuracy of our best GRU model was 93.4%. We also computed F1 scores with respect to both classes. The formulas for precision recall in an F1 score are shown here with respect to the positive class. Inverting the positives with negatives in these formulas will allow you to compute an F1 score for the negative or benign class. Our model achieved an F1 score of 0.930 for the malicious class and 0.931 for the benign or negative class. Given it is composed of both precision and recall, an F1 score provides a holistic measure of how well a model performs on a given class. The fact that our scores are similar and both relatively close to 1 is a good sign, because we want our model to both recognize malicious URLs and avoid blocking legitimate ones.
We also trained a decision tree baseline model on pre-computed features of a URL. This model achieved a test accuracy of 82.2% and the following F1 scores. Our GRU model clearly outperforms the baseline model. However, the GRU accuracy is still lower than the accuracies achieved by many researchers in the academic literature. This can be attributed to the limitations of our dataset that we discussed earlier. For example, the removal of HTTPS is problematic, as we found in research that this can be a sign it is not malicious. From this, we learned a key lesson. Bigger datasets are not always better if quality is compromised. Let's say you're a U of T student wanting to do APS 360 homework, so you navigate to Quarkus. As you can see from the collab output, the model has determined that this website is safe. You then check your uToronto webmail. You have received a suspicious email. Thankfully, the model has successfully detected the malicious URL, and so you can mark it as spam. The model was able to do this despite having never seen the Quarkus URL nor the malicious URL. This is the power of machine learning, and that concludes this presentation. We hope you enjoyed listening.